Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Waves. Waves transfer energy without transferring matter. Waves are classified into two types: transverse waves and longitudinal waves. Transverse waves. In transverse waves, the direction of vibration is perpendicular to the direction of propagation, or direction of energy transfer, or the direction of wave traveled. For example, water waves, seismic secondary waves, slinky waves and electromagnetic waves. We can demonstrate the transverse wave by shaking the spring up and down, as shown. Direction of vibration is up and down, which is perpendicular to the direction of wave propagation, or direction of energy transfer, or direction of wave traveled, is to the right. Direction of vibration is up and down, around the equilibrium position. This is the equilibrium position. When the wave vibrates for one cycle, it creates one wave that travels one wavelength. The red particle at the red arrow is moving up and down. This shows that wave transfers energy without transferring matter. Highest peak is called a crest. Lowest peak is called a trough. Longitudinal waves. In longitudinal waves, the direction of vibration is parallel to the direction of propagation, or direction of energy transfer, or the direction of wave traveled. For example, sound waves, slinky waves and seismic primary waves. We can demonstrate a longitudinal wave by shaking the spring forward and backward, as shown. Direction of vibration is forward and backward, which is parallel to the direction of wave propagation, or direction of energy transfer, or direction of wave traveled, is to the right. Direction of vibration is forward and backward, around the equilibrium position. This is the equilibrium position. When wave vibrate for one cycle, it creates one wave that travels one wavelength. Where the spring compresses together, this is called a compression. Where the spring extends apart, this is called a rarefaction. Compression is where wave particles are close together and high pressure or high density. Rarefaction is where wave particles are far apart and low pressure or low density. Describing waves. Here is the graphs of displacement time graph of a traveling wave. Here is the displacement distance traveled graph of a traveling wave. Amplitude, A, of a wave is the distance from equilibrium position to the peak of the wave. It represents energy carried by the wave, so a wave with a high amplitude carries a lot of energy. Wavelength, lambda, of a wave is the distance between consecutive peaks, or between consecutive identical points. It is measured in meters, m. Frequency, f, of a wave is the number of vibrations per second or numbers of waves that travel past a point per second. It is measured in hertz Hz. Period, t, of a wave is the time taken for one vibration to completely or for one wave to travel past a point. It is measured in seconds, s. If a water wave travels n waves in t seconds, its frequency is n to divide by t. Its period is t to divide by n. So, frequency is 1 to divide by period. Speed, v, of a wave is the distance traveled by wavefront per unit time. It is measured in meters per second. If the distance traveled is one wavelength, then the time taken is one period. Since 1 over period is equal to frequency, then speed is equal to wavelength times frequency. Wavefronts of wave are the lines along peaks, compressions, or rarefactions of the wave are aligned. Demonstrating the wavefronts of the water wave in a ripple tank. A ripple tank is a shallow tray of water, with a light source shining down through it. The light illuminates the wavefronts, making them visible. A straight dipper can be used to create straight wavefronts in a ripple tank. When the dipper is vibrated up and down, It creates a series of parallel wavefronts. The screen below the ripple tank is used to observe the wavefronts of the water wave. The stroboscope, or video camera, is used to make the slow motion of the wavefronts of water wave on the screen. A small sphere dipper can be used to create circular wavefronts in a ripple tank. When the dipper is dropped into the water, it creates a circular wavefront that expands outward, as shown. The side view of the water wave in the ripple tank. The top view of the water wave in the ripple tank. We see the wavefronts are straight along crests, or troughs of the wave. So, the distance between consecutive wavefronts is wavelengths. Because of the wavelength, is the distance between two consecutive crests, or troughs of the wave. The direction of propagation, or direction of energy transfer, or direction of wave traveled, is always perpendicular to the wavefronts. Reflection of waves. When waves hit an obstacle, they are reflected. The direction of the wave propagation changes, but the speed, wavelength, and frequency remain constant. Demonstration of wave reflection using a ripple tank. The incident wavefront hits the obstacle, creating the reflected wavefront, as shown. When the series of incident wavefronts hit the obstacle, creating the series of reflected wavefronts, as shown. Candidates should be able to draw the diagram of this reflection. Draw the incident wavefronts and the reflected wavefronts. The angle between the incident wavefronts and the surface of obstacle is equal to the angle between the reflected wavefronts and the surface of obstacle. Draw the incident ray that is perpendicular to the incident wavefronts, and its direction is the direction of wave propagation, direction of energy transfer. Draw the normal line at right angle to the surface of the obstacle. The angle of incidence, I, is between the incident ray and normal line. Draw the reflective ray that is perpendicular to the reflected wavefronts, and its direction is the direction of wave propagation, direction of energy transfer. The angle of refraction, R, is between the reflective ray and normal line. Space between consecutive wavefronts is wavelength, which are equal before and after reflection. Rules of the reflection. The angle of incidence, I, is equal to the angle of reflection, R. The incident ray, reflective ray, and normal lie on the same plane. Circular wavefronts can be reflected at a flat obstacle, as shown. The circular wavefronts is created from source, S. They reflect at the flat obstacle. The image of the source, R, is created behind the obstacle, which the reflected waves appear to come. Refraction of waves. When waves travel through one medium to another, they are refracted. This is because the speed of wave is changed, causing its wavelength also change, while its frequency remain constant. Demonstration of wave refraction using a ripple tank. This area is shallow water and this area is deep water. In a shallow water, place the glass block in the water. The water waves travel slow in shallow water due to the friction increase, so its wavelength also decreases, while constant frequency. The water travel fast in deep water due to the friction decrease, so its wavelength increases, while constant frequency. The incident wavefronts travel from deep water to shallow water. The wave speed decreases to cause the wavefronts bend toward the normal line, and they are close together. This causes the wavelength to decrease. Candidates should be able to draw the diagram of the refraction of wave. This is the boundary between shallow and deep water. This region is deep water. This region is shallow water. Draw the incident wavefronts of wave in deep water. Draw the refractive wavefronts of wave in shallow water. Draw the direction of incident ray at perpendicular to the incident wavefronts. Draw the normal line at perpendicular to the surface of the boundary. Draw the refractive ray at perpendicular to the refracted wavefronts. The angle of incidence, I, is between the incident ray and normal line. The angle of refraction, R, is between the refractive ray and normal line. When the water wave travel from deep water to shallow water at perpendicular to the surface of boundary as shown. This region is shallow water. This region is deep water. The wavefronts are not bent, but the wavefronts are close together. This shows that wavelength decreases due to the wave speed decreases when travel from deep to shallow water. Draw the diagram to show the refraction of wave of this situation. This region is deep water. This region is shallow water. Draw the incident wave fronts of wave in deep water. Draw the refractive wave fronts of wave in shallow water. Draw the direction of incident ray at perpendicular to the incident wave fronts. Draw the normal line at perpendicular to the surface of the boundary. Draw the refractive ray at perpendicular to the refracted wave fronts. The angle of incidence is between the incident ray and normal line to be 0. The angle of refraction is between the refractive ray and normal line to be 0. Therefore, the refractive ray is not bent when the incident ray travels along the normal or perpendicular to the boundary. This is because the angle of incidence and angle of refractive are equal to 0. Diffraction of waves. Diffraction is the spreading out of waves as they pass through a gap or around an obstacle. After diffraction, the speed, wavelength, and frequency of the waves remain constant. The amount of diffraction depends on the wavelength of the wave compared to the size of the gap or obstacle. More diffraction occurs when the wavelength is similar to the size of the gap or obstacle. Less diffraction occurs when the wavelength is much smaller than the size of the gap or obstacle. Demonstration of wave diffraction using a ripple tank. When the size of gap is similar to wavelength, as shown. Straight wave fronts pass through the gap. Waves spread out more, causing the straight wave fronts to become curve. Space between each wave fronts are equal, this shows that wavelength remains constant. When the wavelength decreases, while the size of gap remain constant, as shown. Waves spread out less, causing the refractive wave fronts are less curved. This shows that the waves diffracted less. Candidates should be able to draw the diffraction. When the wavelength is similar to the size of gap. Draw the obstacles and their gap. Draw the straight wave fronts of wave that has wavelength is similar to size of gap. Draw the curved wave fronts of wave that spread out with same wavelength before diffraction. When the wavelength decreases, while the size of gap remains constant, as shown. Draw the obstacles and their gap. Draw the straight wave fronts of wave that has wavelength is much smaller than the size of gap. Draw the diffracted wave fronts of wave that spread out with same wavelength before diffraction. This region is not diffraction because the wave fronts are straight, showing wave not spread. This region is spread out, showing wave is diffracted. When waves pass through the edge of obstacle, as shown. Waves diffract at the edge of obstacle. When wavelength decreases, causing the amount of diffraction decreases. Candidates should be able to draw the diffraction of waves around an obstacle. Draw an obstacle. Draw the straight wave fronts of waves with its wavelength lambda. Draw the diffracted wave fronts that spread out around the edge of the obstacle. When the wavelength decreases, causing the amount of diffraction decreases. Draw an obstacle. Draw the straight wave fronts of waves with its wavelength lambda. Draw the diffracted wave fronts that spread out around the edge of the obstacle. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. General properties of light waves. Light waves are the transverse waves and electromagnetic waves. so light can transfer energy through the vacuum. Speed of light in the vacuum is 3 times 10 to the power of 8 meters per second, which is approximately equal to speed of light in air. Light is travel in the straight line. Light wave exhibits the reflection, refraction and diffraction. We will explain the reflection and refraction later, but the diffraction of light will be studied in A-level physics. Reflection of light. From the previous section of 3.1 Properties of waves, we know the rules of reflection that the angle of incidence, I, is equal to the angle of reflection, R. The incident ray, reflective ray, and normal lie on the same plane. From this rule, candidates should be able to draw the diagram of reflection of light on plane mirror. Here is the plane mirror. Here is an object. Draw the incident ray from the top of an object to anywhere on the plane mirror. Draw the normal line at right angles to the plane mirror. Measure the angle of incidence, I, between the normal line and the incident ray. Measure the angle of reflection, R, between the normal line and the reflective ray. Both angles must be equal. Draw the reflective ray. Extend the reflective ray back behind the plane mirror as dotted line, this shows it is virtual ray. Draw the second incident ray from the top of the object to anywhere on the plane mirror. Repeat the steps from the normal line and reflective ray for the second incident ray. The virtual image is created behind the plane mirror at the intersection of both dotted lines. We can see the image when the reflective rays travel toward our eyes. This image is virtual, because it can only be seen by the eye. It cannot be focused onto a screen, which is why it is virtual. The characteristic of the virtual image. The image is as far behind the mirror as the object is in front. The image is the same size as the object. The image is laterally inverted, which means left and right are swapped around. The image is right way up, or upright, as the object. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Refraction of light. Light will refract when it travels through the transparent materials, such as glass. Angle of incidence is denoted by I. Angle of refraction is denoted by R. As the incident light ray enters the glass block, it slows down and bends towards the normal. As the light ray leaves the glass block, it speeds up and bends away from the normal. The frequency of light is unchanged as it travels from one medium to another. The wavelength of light changes directly with the speed of light. As the light speeds up, the wavelength increases. As the light slows down, the wavelength decreases. When light travels from an optically less dense medium to a more dense medium, it slows down and so bends towards the normal. When light travels from a more dense to less dense medium, it speeds up and bends away from the normal. If the angle of incidence is 0 degrees, the ray enters along the normal to the surface of the glass block. The light slows down but does not change direction, because the angle of refraction is also 0. As it leaves, it speeds up, but does not change direction. Refractive index. Refractive index, N, of a material, is the ratio of speed of light in a vacuum, c, to speed of light in the material, v. We can write the equation of refractive index as N equals c over v, where N is a refraction index, which is a constant for the medium and has no unit. C is the speed of light in vacuum, which is equal to 3 times 10 to the power of 8. V is the speed of light in a medium. The refraction index in air is approximately equal to 1, because speed of light in air is very close to the speed of light in vacuum. The refractive index of a material is related to how dense it is. Generally, the denser the material, the higher the refractive index. For example, the light ray in the medium A bends less than the light ray in the medium B. So, the speed of light in the medium A is more than the speed of light in the medium B. This shows that the medium A is less dense than the medium B. Therefore, the refractive index in the medium A is less than in the medium B. Snell's law. Snell's law is a formula used to describe the relationship between the angles of incidence and refraction. N1 sin I equals N2 sin R, where N1 is the refractive index in the first medium that light passes. I is the angle of incidence. N2 is the refractive index in the second medium that light passes. R is the angle of refraction. When light travels from air to a medium, N1 is refractive index in air, which is equal 1. So the formula becomes N equals sin I over sin R. Example 1. A ray of light is incident in air on a glass at an angle of 60 degrees to the normal. The refractive index of glass is 1.5. Calculate the angle of refraction. From Snell law. Substitute N1 equals 1 for air. I equals 60. And N2 equals 1.5 for glass. So, sin R equals sin 60 over 1.5. Then calculate R to get R equals 35.3 degrees. Example 2. A ray of light in water incident to the air at the refractive angle of 70 degrees. The refractive index of water is 1.3. Calculate the angle of incidence. From Snell's law. Substitute N1 equals 1.3 for water. N2 equals 1 for air. And R equals 70 degrees. So, sin I equals sin 70 over 1.3. Then calculate R to get R equals 46.3 degrees. Example 3. A ray of light in air incident to the diamond at the incident angle of 47 degrees and the refractive angle of 15 degrees. Calculate the refractive index and the speed of light in the diamond. From Snell's law. Substitute N1 equals 1 for air. I equals 47 degrees. And R equals 15 degrees. So, N equals sin 47 over sin 15. N equals 2.8. From N equals C over V. So, V equals C over N. Substitute N equals 2.8. And C equals 3 times 10 to the power of 8. Then, V equals 1.07 times 10 to the power of 8 meters per second. An experiment to investigate the reflection of light and calculate the speed of light in the glass. Place a glass block on a piece of paper and trace around the block with a pencil. Shine a ray of light in air on the glass block. Place 2 pins along the incident ray, with a separation of more than 5 centimeters to ensure accuracy when drawing the line. Place 2 pins along the emerging ray from other side of glass block, with a separation of more than 5 centimeters. Remove the glass block and pins, then mark at the pins holes. Turn off the light box. Use a ruler to draw the incident ray and the emerging ray. Then, connect the entry and exit points to show the path of light within the glass block. Draw the normal line at the point of incidence. Measure the angle of incidence, I, and the angle of refraction, R. Calculate the refractive index of the glass using N equals sin I over sin R. Calculate the speed of light in the glass using the formula V equals C over N. Repeat the experiment for 5 different angles of incidence, and then find the average of refractive index and speed of light in the glass. Or, plot the graph of sin I against sin R Then find the refractive index by the gradient of graph. Calculate the speed of light in the glass using V equals c over n. The critical angle and the total internal reflection in a medium. As the rays shine on the semicircle glass block, the light slows down, but does not change direction. This is because the angle of incidence is 0 degrees, the ray enters along the normal to the surface of the glass block, then the angle of refraction is also 0. As the ray reach the point A, some ray reflect and some ray refract. When a ray of light travels from a denser medium, glass, to a less dense medium, air, it bends away from the normal. As the angle of incidence, I, increases, the angle of refraction, R, increases. The intensity of refractive ray decreases, while intensity of reflective ray increases. When R equals 90 degrees, the angle of incidence is equal to the critical angle, C. Therefore, the critical angle is the angle of incidence in denser medium, where the angle of refraction is 90 degrees. We can calculate the critical angle using the equation sin of C equals 1 over n. If the angle of incidence is increased beyond the critical angle, total internal reflection occurs. The total internal reflection occurs when the light ray travels from denser medium to less dense medium. The angle of incidence is more than the critical angle of the medium. No refraction of light. The angle of incidence is equal to the angle of reflection. Uses of the total internal reflection in everyday life. Periscope consists of the glass prisms, which are used in submarines. As a light ray travels through a periscope, total internal reflection occurs at point A and point B. A glass right-angle prism with an angle 45 degrees. The critical angle of glass is about to 42 degrees. As the light ray travels from air to glass at the angle of incidence is 0, so the light slows down, but does not change direction. The light ray reflects at the point A with the incident angle of 45 degrees, which is greater than the critical angle of glass, 43 degrees. This causes the light ray to undergo total internal reflection. As it leaves the prism, it speeds up, but does not change direction. Binocular consists of the prisms, as shown. As the light ray travels through a binocular, and the total internal reflection occurs at points A, B, C and D. The prisms in this binocular are glass right-angle prism 45 degrees. As the light ray travels from air to glass at the angle of incidence of 0, so the light slows down, but does not change direction. The light ray reflect at the point A with the angle of incidence is 45 degrees, which is greater than the critical angle of glass. This causes the total internal reflection to occur. Then the light ray reflect at the point B with the angle of incidence is 45 degrees, which is greater the critical angle of glass. This causes the total internal reflection to occur again. As it leaves from the prism, it speeds up, but does not change direction. Rear reflector. Rear reflectors use total internal reflection to reflect light back to the source. They are often used on vehicles to improve their visibility to other road users. Optical fibers. An optical fiber is a thin glass cylindrical core coated with a transparent material of lower refractive index, cladding. The cladding has a lower refractive index than the core, so it is less dense. This means that total internal reflection will occur for all rays of light that strike the boundary between the core and cladding at an angle greater than the critical angle. Optical fibers can be used to communicate signals, for example telephone conversations, or in medical applications, such as endoscopy, a method of examining inside the body. In the communications, optical fibers are used in the TV, internet, and phones. Light or infrared carries the information along the optical fibers. They can carry a large amount of information at very high speed. In medicine, optical fibers are used in the endoscopes, that allow the surgeons to see inside the body of their patients. Light ray from the outside is transmitted through the optical fibers and undergo total internal reflection, which prevents them from leaving the optical fibers. Light ray reflected at the inside the body and return back to the outside along the other optical fibers. This light is sent to the computer monitor or a doctor. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Lens diagram can be described using the following term. Principal axis, a line which passes through the center of a lens. Principal focus, or focal point, the point at which ray of light traveling parallel to the principal axis intersect the principal axis and converge. Focal length, the distance between the center of the lens and the principal focus. Converging lens. In a converging lens, parallel rays of light are brought to a focus. This point is called the principal focus. The distance from the center of lens to the principal focus is called the focal length. The line that passes through the center of a lens is the principal axis. Diverging lens. In a diverging lens, parallel rays of light are made to spread out from a point. This point is the principal focus. It is the point from which the rays appear to diverge from. The distance from the center of lens to the principal focus is called the focal length. The line that passes through the center of a lens is the principal axis. The images produced by lenses can be one of two types: a real image and a virtual image. Real images. A real image is defined as an image that is formed when the light rays from an object meet each other and can be projected onto a screen. Virtual images. A virtual image is defined as an image that is formed when the light rays from an object do not meet, but appear to meet behind the lens and cannot be projected onto a screen. Images from converging lens. Lenses can be used to form images of objects placed in front of them. The location and nature of the image can be found by drawing a ray diagram. When an object beyond 2f, where f is focal point. Start by drawing a ray going from the top of the object through the center of the lens. This ray will continue to travel in a straight line. Draw a ray going from the top of the object, traveling parallel to the axis to the lens. When this ray emerges from the lens, it will travel directly towards the principal focus. Next, draw a ray going from the top of the object through the principal focus until the center of lens, then traveling parallel to the axis to the lens. The image is found at the point where the above three rays meet. In this case, the image is real, diminished, smaller, inverted, and it is between f and 2f. When an object is 2f, the image is real, same size as the object, inverted, and it is at exactly 2f. When an object between 2f and f, the image is real, enlarged, inverted, and it is beyond 2f. When an object is f, the image can be not focused, because rays are parallel, not meet together. When an object between f and lens, start by drawing a ray going from the top of the object through the center of the lens. This ray will continue to travel in a straight line. Draw a dashed line continuing this ray upwards. Next, draw a ray going from the top of the object, traveling parallel to the axis to the lens. When this ray emerges from the lens, it will travel directly through the principal focus f. Also, draw a dashed line continuing this ray upwards. The image is the line drawn from the axis to the point where the two dashed lines meet. In this case, the image is virtual. The light rays appear to meet when produced backwards. Enlarged. upright, and the image is formed on the same side of the object. This case is the use of a single lens as a magnifying glass. We can see that the image moves away from lens, and its size increases when the object moves toward the lens, while the image moves toward the lens, and its size decreases when the object moves away from the lens. Correcting sight. Correcting short-sightedness. People who are short-sighted cannot see things that are far away, and only see things that are close to them. This is because the eye refracts the light and brings it to a focus before it reaches the retina. This can be corrected by using a diverging lens to refract the light and bring it on the retina. Correcting long-sightedness. People who are long-sighted cannot clearly see things that are close, and can only clearly see things that are far away. This is because the eye refracts the light rays and they are brought to a focus beyond the retina. This can be corrected by using a convex or converging lens to refract the light and bring it on the retina. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Dispersion of light. Dispersion of light is the spreading out of white light into the colors of the spectrum. White light may be separated into all its colors by passing it through a prism. White light, or visible light, is a mixture of all the colors of the spectrum. Each color has a different wavelength and frequency, making up a very narrow part of the electromagnetic spectrum. This can be demonstrated experimentally using a triangular glass prism. When white light passes through a triangular glass prism, it refracts at each surface and is deviated through a large angle. All of the colors that make up white light. Violet travels slowest in glass, and red travels fastest in glass. This means that violet is bent through the largest angle and red through the smallest. The other colors of visible light appear in between, and so a spectrum is seen on the screen. So, the refraction index of glass is higher for violet light than for red light. Visible spectrum of light. Visible light is defined as the range of wavelengths which are visible to humans. In the natural world, many animals, such as birds, bees and certain fish, are able to perceive beyond visible light and can see infrared and UV wavelengths of light. The different colors of waves correspond to different wavelengths. Red has the longest wavelength and the lowest frequency and energy. Violet has the shortest wavelength and the highest frequency and energy. Monochromatic light. It is the light of a single frequency or wavelength, meaning that it has only a single color. For example, a laser beam is monochromatic light. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Electromagnetic spectrum. All electromagnetic waves have the following properties. They are all transverse waves. They can all travel through a vacuum. They all travel at the same speed in a vacuum. Its speed in a vacuum is 3 times 10 to the power of 8 meters per second and is approximately the same in air. The electromagnetic spectrum is arranged in a specific order based on the wavelengths or frequencies. The main groupings of the continuous electromagnetic spectrum are radio waves, microwaves, infrared, visible light, red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-rays, gamma rays. This order is shown in the diagram from longest wavelength to shortest wavelength, lowest frequency to highest frequency, lowest energy to highest energy. Size of wavelength of radio wave is approximately to the size of the building. Microwave is approximately to the size of baseball. Infrared is approximately to the size of pinpoint. Visible light is approximately to size of the bacterial. Ultraviolet is approximately to size of virus. X-rays is approximately to size of atom. Gamma rays is approximately to size of subatomic particles. The higher the frequency, the higher the energy of the electromagnetic waves. Electromagnetic wave with higher energy is highly ionizing, harmful to cells and tissues causing cancer, such as UV, X-rays, and gamma rays. Electromagnetic wave with lower energy is less ionizing, less harmful to humans, such as radio waves, microwaves, infrared and visible light. Useful for communications. Uses of electromagnetic waves. Electromagnetic waves have a variety of uses and applications. Radio waves. Communication. Radio waves are used to transmit the signal of radio and television. They are also used in cellular networks, GPS, and Wi-Fi. Radio frequency identification uses radio waves to identify people or objects. They are used in a variety of applications, such as inventory tracking, access control, and payment systems. Bluetooth is used to communicate between two Bluetooth-compatible devices. Astronomy. Radio telescopes are used to observe the naturally occurring radio waves that come from stars, planets, galaxies, and other astronomical objects. Microwaves. Communication. Microwaves are used to transmit the signal of satellites, television, and mobile phones. They are also used in radar systems. Cooking. Microwaves are used to heat food in microwave ovens. They work by causing the water molecules in food to vibrate, which creates heat. Infrared is emitted by warm objects. Electric grills. Some electric grills use infrared heat to cook food. Remote controls. Remote controls use infrared light to send signals to devices such as TV. Intruder alarms are the motion sensor. Thermal imaging. Infrared cameras can be used to create images of objects that emit infrared radiation. This can be used for medical imaging, security, and industrial applications. Optical fibers. Optical fibers are used to transmit the signal in the communication, which is more efficiently than visible light. Visible light. Seeing. Visible light is the part of the electromagnetic spectrum that can be detected by the human eye. It is used for vision, photography, and videography. Communication. Visible light can be used to transmit data in optical fibers. Ultraviolet. Fluorescence. Some substances glow when they are exposed to ultraviolet light. This can be used to create security markings and detect fake bank notes. Tanning. Ultraviolet light from the sun can cause tanning. It can also cause skin cancer. Sterilization. Ultraviolet light can be used to sterilize surfaces and kill bacteria. It is used in hospitals, laboratories, and food processing plants. X-rays. Medical imaging. X-rays are used to create images of the inside of the body. They are used to diagnose diseases and injuries. Security scanning. X-rays are used to scan luggage and people at airports and other security checkpoints. Gamma rays. Sterilizing food and medical equipment. Gamma rays can be used to bacteria and living things. Cancer treatment. Gamma rays are used to kill cancer cells. Harmful effects of electromagnetic waves on people. The higher the frequency of an electromagnetic wave, the higher its energy. Electromagnetic wave with higher energy is more ionizing, meaning that it can remove electrons from atoms or molecules. This can be harmful to cells and tissues, and can even cause cancer. Electromagnetic wave with lower energy is less ionizing and is less harmful to humans. It can still be harmful, however, if it is absorbed in large amounts. Beyond the visible part of the spectrum, the energy becomes large enough to ionize atoms. The main risks associated with electromagnetic waves are summarized as radio waves. No known danger. Microwave. Possible heat damage to internal organs, when the water molecules in the body absorb microwaves strongly. Infrared. Infrared can cause heating effects in tissues, meaning it can also cause skin burns, but it is less likely to cause internal damage than microwaves. Visible light. Very bright light can cause eye damage. This is because the retina of the eye is sensitive to light. Ultraviolet. If eyes are exposed to high levels of UV, it can cause severe eye damage. Skin cancer. Ultraviolet is ionizing, meaning it can kill cells or cause them to malfunction, resulting in premature aging and diseases such as skin cancer. X-rays. X-rays are the most ionizing radiation, meaning they are able to penetrate the body and cause internal damage, so they are caused to kill cells. Mutation of genes and cancer. Gamma rays. The harmful effects of gamma rays like as X-rays, because they are the most ionizing radiation, so they are caused to kill cells. Mutation of genes and cancer. It is important to note that the harmful effects of electromagnetic waves depend on the amount of radiation that is absorbed. A small amount of radiation may not be harmful, but a large amount of radiation can be very harmful. The risk of harm also depends on the type of tissue that is exposed to the radiation. For example, the retina of the eye is more sensitive to light than other tissues, so it is more likely to be damaged by exposure to visible light. The best way to protect yourself from the harmful effects of electromagnetic waves is to limit your exposure. This means avoiding using electronic devices for long periods of time, staying away from sources of strong radiation, and wearing protective clothing when necessary. Communications with satellites. Geostationary and polar orbiting satellites are both used for communication. Geostationary satellites orbit above the Earth's equator. The orbit of the satellite is 24 hours. At a height of 36,000 kilometers above the Earth's surface, much higher than polar satellites. Used for radio and telecommunication, broadcasting around the world due to its high orbit. Polar, or low orbit, satellites orbit around the Earth's north and south poles. These orbit much lower than geostationary satellites, at around 200 kilometers above sea level. Used for monitoring the weather, military applications, and taking images of the Earth's surface. There is a much shorter time delay for signals compared to geostationary orbit signals. The signals and images are much clearer due to the lower orbit. However, there is limited use in any one orbit, because more than one satellite is required for continuous operation. System of communications. Many important systems of communications rely on long wavelength electromagnetic radiation, including Bluetooth use radio waves to transmit information between electronic devices over short distances, such as phones and speakers. This is because radio waves pass through walls, but the signal is weakened on doing so. Mobile phones and wireless internet use microwaves, because microwaves can penetrate some walls and only require a short aerial for transmission and reception. Optical fibers are used for cable television and high-speed broadband, because glass is transparent to visible light, and some infrared, visible light, and short-wavelength infrared can carry high rates of data. Digital and analog signal. Analog signals vary continuously, they can take any value. Examples of analog technology include telephone transmission and some broadcasting. A digital signal can only take one of two discrete states. These are usually referred to as 1 and 0, high and low, or on and off. The key advantages of transmission of data in digital form compared to analog are: the signal can be regenerated, so there is minimal noise. Due to accurate signal regeneration, the range of digital signals is larger than the range of analog signals. They can cover larger distances. Digital signals enable an increased rate of transmission of data compared to analog. Extra data can be added so that the signal can be checked for errors. Sound waves that can be transmitted as a digital or analog signal. Signals for speech or music are made up of varying frequencies. In order to make out the information clearly, the signal needs to be transmitted with as little interference as possible. The signal is converted both before transmission and after being received. Before transmission, the signal is converted from analog to digital. After being received, the signal is converted from digital to analog. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Describing sound wave. Sound wave is the longitudinal wave, which means that the particles of the medium vibrate in the same direction as the wave is traveling. Sound waves are produced by vibrating sources. When a vibrating source moves back and forth, it creates pressure variations in the surrounding medium. Sound waves require a medium to transfer their energy. The medium can be air, water, or any other solid or liquid. This is why sound cannot travel through a vacuum. The sound travels faster in solids than in liquids, and faster in liquids than in gases. The speed of sound in air is approximately to 330 meters per second. The speed of sound in liquids is approximately to 1,500 meters per second. The speed of sound in solids is approximately to 300 to 500 meters per second. The explanation of how a source, such as a drum, produces sound. When you bang a drum, the skin vibrates. The vibrating drum skin causes nearby air molecules to vibrate. This is because the air molecules are bumping into each other. The vibrating air molecules cause other nearby air molecules to vibrate, and so on. This creates a series of compressions and rarefactions in the air. The compressions are regions where the air molecules are closer together and high pressure. The rarefactions are regions where the air molecules are farther apart and low pressure. The compressions and rarefactions travel through the air as sound waves. The distance between the consecutive compressions or consecutive rarefactions is the wavelength. The harder you bang, the bigger the vibrations, and the louder the sound. This causes the air molecules to be closer together in the compressions and farther apart in the rarefactions. The greater the difference between the air pressure in the compressions and rarefactions, the louder the sound. An experiment to determine the speed of sound in air. The speed of sound in air is approximately 330 meters per second at 25 Celsius. Speed of sound in the hot air is faster than in the cold air. This is because the air particles in hot air have higher speed than the cold air. So, the speed of sound in air varies from 330 to 350 meters per second. Investigate the speed of sound between 2 points. Two people stand a distance of around 100 meters apart. The distance between them is measured using a tape measure. One person has two wooden blocks, which they bang together. The second person has a stopwatch, which they start when they see the first person banging the blocks together, and stops when they hear the sound. This is then repeated several times, and an average value is taken for the time. The speed of sound can then be calculated using the equation. Speed is equal to the distance traveled by sound to divide by time taken. Investigate the speed of sound using the echoes of sound. The echoes of sound is caused by the reflection of sound. A person stands about 50 m away from a wall using a tape measure to measure this distance. The person claps 2 wooden blocks together and listens for the echo. A second person has a stopwatch and starts timing when they hear one of the claps and stops timing when they hear the echo. The process is then repeated 5 times and an average time calculated. The distance traveled by the sound between each clap and echo will be 2 times 50 meters. The speed of sound can be calculated from this distance and the time using the equation. Speed is equal to the twice of distance to the wall and divide by echo time. The echo time is time that the sound travels forward and backwards. The diffraction of sound. Sound can diffract around the corner of the building or through doorway. This is because the wavelength of a sound is similar to the size of door gap or the corner of the building. When a person is walking on the other side of building, he can hear the sound from the radio, because the sound from the radio diffracts around the corner of the building. When a person is the outside of the room that the door is opened, he can hear the sound from the television inside the room. This is because the sound can diffract through the doorway. Pitch and loudness of sound. The frequency of a sound wave is related to its pitch. Sounds with a low pitch have a low frequency, or long wavelength. Sounds with a high pitch have a high frequency, or short wavelength. The amplitude of a sound wave is related to its volume. Sounds with a large amplitude have a high volume. Sounds with a small amplitude have a low volume. Ultrasound. Ultrasound is the name given to sound waves with a frequency greater than 20,000 Hz. Humans can hear sounds between about 20 Hz and 20,000 Hz in frequency, although this range decreases with age. So, the frequency of ultrasound is beyond the range of human hearing. The sound with frequency lower than 20 Hz is called the infrasound. The uses of ultrasound. Sonar stands for sound navigation and ranging for the boat and some animals. Bats and dolphins use a similar method, called echolocation, to detect their surroundings and to find food. Sonar and the echo sounding can be used to measure depth, or to detect objects underwater. A sound wave can be transmitted from the surface of the water. The sound wave is reflected off the bottom of the ocean. The time it takes for the sound wave to return is used to calculate the depth of the water. The distance the wave travels is twice the depth of the ocean. This is the distance to the ocean floor plus the distance for the wave to return. The depth of the water can then be calculated using the equation. Speed equals the twice of the depth to divide the echo time. Medical scanning of soft tissue. To construct images of a fetus in the womb. To generate 2D images of organs and other internal structures, as long as they are not surrounded by bone. Cleaning and breaking. Using ultrasound, delicate machinery can be cleaned without dismantling it. Ultrasound can be directed to very precise areas and be used to vibrate dirt away. This is also used for cleaning teeth. Ultrasounds can remove tartar. This can lead to gum disease. In hospitals, concentrated beams of ultrasound can be used to break up kidney stones and gallstones without patients needing surgery. Check for cracks inside metal objects. A crack in a metal block will cause some waves to reflect earlier than the rest, so will show up as pulses on an oscilloscope trace. Each pulse represents each time the wave crosses a boundary. The speed of the waves is constant, So measuring the time between emission and detection can allow the distance from the source to be calculated. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.